What is up, guys? In this Supp video, we will be talking about P series, which is a really fast and easy and fun test, along with DCT. Okay, because I just remembered we need P series to do DCT. So let's talk about P series first, okay, and why it's called P series and where it comes from and all that stuff. All right, so P series. P series talk about series in the form of 1 over n to the power of p. Usually starts from 1 to infinity. Usually starts from 1. The index starts from 1, goes all the way up to infinity, right? And p is going to be is an integer. An integer? No, I'm sorry. No. P is a real number. My bad. P is a real number. Okay? Could be anything it wants. And I'm just going to tell you guys that if you look at specific values of P, we've looked at 2 already from last lecture, right? We saw that 1 over n diverged and 1 over n squared converged, right? Using integral tests in the notes from last class, all right? So there is this kind of like phenomena that happens here, that as soon as you pass over the value of 1 and go on to anything greater, that means like 1.00000 like 1, right? Like as soon as you tip over, something really interesting happens. The series actually starts to converge, which is really cool. So basically, P series it boils down into 2 cases. If P is less than or equal to 1, we can actually just say that 1 over n is divergent. Right? You can prove this with using the integral test on just like P instead of like a specific value of P, but we're not really going to do that here. So, and then if P is greater than 1, you get the convergent case. So what does this mean? I can just say straight up that, so like, if I have 1 over n to the 4th power, there's a really quick example. I can just say, since P is greater than 1, sum of 1 over n to the 4th is convergent. How do I know? By P series. That's it. These problems are nice, fast, and simple. And what's really cool is like you use the integral test to kind of get to this conclusion. I wish we had more time in class to like talk about that stuff, but I want to talk about DCT. So that's it. That's pretty much it for P series. So we're going to use these P series for DCT problems, okay? So let's talk about DCT. I won't go too crazy into DCT. I just want to show you some really basic examples of DCT. All right, so DCT, it stands for the direct comparison test. And it's actually going to use those 2 diagrams I showed in class, last class, right? Where we have like a known. This is like a known. I'm gonna call this. Let's call this a sub n, and this sum of a sub n converges, right? And we were talking about last class that if it falls below or falls above, your conclusion is based off of your assumption, right? This is our assumption. Your conclusion is based off of the assumption. So in this case, if I have a b sub n, right? I can say that b sub n converges as well. Why? For the same exact reasoning that we talked about in class. If all the values fall below something that we know converges, then we can actually just say b sub n converges also. And the idea of this is actually just DCT. So putting it all together, right? The first scenario is if the sum of a sub n converges and the sum of a sub n, I'm sorry, we actually don't even need the sum. We just need the sequence, right? The other way. The a sub n is greater than b sub n. Then we can say the sum of b sub n converges by DCT. All right, I'm gonna expand on this. That's it. That's the first half of DCT. You guys can probably guess what the other half of DCT is, but I'm gonna expand on this just a little bit further, just to once again line up with what we were talking about in class. If I have a C sub n, another sequence, right, that falls above A sub n, we know that C sub n will be inconclusive. Okay, so if that's the case, you actually cannot use DCT. So that's kind of like the catch with this. You need to show, this implies you need to show, like, I guess you could say you need to prove, but you need to show that A sub n is greater, did I screw that up? No, greater than B sub n in your work. And I'm going to show you guys that in an example. All right. So that's the first half of DCT. The second half of DCT is, you guys can probably guess, if the sum of A sub n diverges, okay, think back to the picture. I'll just draw the picture here, right? If now the sum of A sub n diverges, right, then we know that anything that falls above will also diverge. If you guys remember, this was the picture I drew in class. And then, of course, anything that falls below is inconclusive. So for the same reasoning, if the sum of A sub n is divergent, then anything that falls above, so this time A sub n is smaller than B sub n, then we can say the sum of B sub n diverges. Why? By DCT. And hopefully that makes sense here. So let's look at a quick example here. If I have time, I'll do two of these. But we're gonna do two examples, one convergent, one divergent case. All right. So let me pull up my example here. I'll call this example woo, because just making this up. So here we go. Let's say I have a series from 1 to infinity of n squared minus 3 this time. Okay, so here we go. We're going to use the DCT on this, all right? So I don't know anything about this series, right? I'm going to label this as A sub n, and this is my unknown. This is the thing I'm trying to figure out, right? So how do we use DCT? We need to see what this series kind of closely resembles, right? And the best way to do that is to look at the powers on top and on the bottom, meaning like the growth rates. Like, what does the top behave like? What does the bottom behave like? And what we can say is that this actually, the bottom here, it behaves like n to the 2/3. Why is that? Well, the -3, the -3, as we go to infinity, becomes irrelevant, right? It doesn't really matter. The only thing that truly influenced that n variable is the 2 and the 1/3 power. So, kind of putting this all together, what we can say is that A sub n kind of looks like 1 over n to the 2/3. And why is this good for us? Right? Why is this good for us? This we know stuff about this. We just talked about this, right? The sum of B sub n, it's a P series. And so, sorry. It's a P series where P is less than or equal to 1. So we can just say that B sub n diverges. All right, so we have our known now, right? A sub n is our unknown. B sub n is now our known. We use the P series to prove that it's divergent. So what does that mean? This is going to fall under the this case, the divergent case, right? We have something that diverges, so we want the thing that we don't know to fall above. How do we show this? We need to show, or we want B sub n to be less than A sub n, right? Because if A sub n falls above B sub n, we can just say that it diverges by direct comparison test. So we're trying to figure this out. So here we go. We have to use some algebra here. I know, right? Scary. 1 over n to the 2/3. Is this less than 1 over n squared minus 3 to the 1/3. Well, let's show this. Let's do some algebra. I'm going to multiply both sides by the common denominator here, right? Or like by the denominators. You get this. I'm gonna cube everything. We get n squared. Is this greater than n squared minus 3? And yeah, this is true for all n values. For all the values on our index from 1 to, is it true for 1? Yeah, it's true for 1, thank goodness. Yeah, it's true for all n values. So it's true from 1 to infinity, which means, so this means, so we just showed that b sub n is in fact less than a sub n. So since b sub n is less than a sub n, and the sum of b sub n diverges, we don't need to say again why. We already said it in our work here, right? We said it by p series. So we don't need to say why b sub n diverges again, but we just have to state that b sub n diverges. So the sum of a sub n, the one that we're trying to figure out, also diverges. And how do we know? By dct. And this is your final line. So what do I need to see when you do dct? I need to see you come up with another sequence to compare to. I need you to make the comparison and show with algebra that it fits what you're trying to do, right? This was the divergent case. And then I need to see your final statement. Okay, I will do one more example, but if you're good with this, you can just stop watching here. All right, but I will do one more example. This one's a fun one because it doesn't use p-series. It uses something else. Here we go. This one is example 3. Whoops, that's the sum sign. This is example 3 on page 578. Here we go. It's from 1 to infinity of 1 over root n 3 to the n. We have 1 over root n 3 to the n. So how do we pick, okay, I'm going to call this a sub n. How do we pick a b sub n to compare this to for this one, right? Once again, you look at the growth rates. You look at the growth rates, right? If you look, the most influencing behavior, the one that influences the most behavior is the 3 to the n, right? If you guys remember, right, what does the graph of root x look like? It looks kind of like, it looks like that, right? Versus 3 to the n, which looks like that. If you just look at the way they're shaped, like if you actually look at their derivatives, right? Which one is more like extreme? Which one grows at a more aggressive rate? It's the 3 to the n. So for this one, for my b sub n, I'm going to choose 1 over 3 to the n because 1, it's the most influential behavior as n goes to infinity. And 2, I know something about 1 over 3 to the n. I can rewrite this as 1 over 3 to the n. And you're like, oh snap, the sum of b sub n is a geometric series with a is equal to 1, r is equal to 1/3, and since absolute value of r is less than 1, the sum of b sub n converges. Right? You guys see how I had my two assumptions, right? It's a geometric series. And then r is less than 1. Absolute value of r is less than 1. Therefore, I said my concluding statement about b sub n. And additionally, this is now our known. Remember, it converges. So that means we only know stuff below it. So when we run dct, what do we want? We want b sub n to be greater than a sub n in this case. Because if that happens, since b sub n converges, a sub n will also converge. So here we go. Let's see this. 1 over 3 to the n. Is this greater than 1 over 3 to the n root n? Well, let's see. Let's multiply some stuff over and things like that. If I multiply both sides by 3 to the n, they're going to actually just cancel out. And then if I multiply both sides by root n, I get is root n greater than 1 for all n greater than or equal to 1. Well, it's not true for 1, but it is true for everything above 1. Wait, no, we don't need... I'm sorry, not greater than equal. Greater than 1. Greater than 1 is fine. Right? Yeah, I guess these can be fine too, right? Because if you have something that converges, and if it equals, then yeah, of course it's also going to be converged. So that's fine too. So is this true for all things greater than 1? Yeah, because root n is going to be greater than 1 for all values, or for everything bigger than 1. So since we have a true statement, since b sub n is greater than a sub n, and the sum of b sub n converges, don't need to say why, the sum of a sub n converges by dct. And that's it. If you guys want, we'll do another example in class on Monday, but like I said, in class today, I wanted to make sure you guys were exposed to this DCT stuff before we talked about it, just so that you guys are ready. All right? Okay, guys, I'll see you guys on Monday. Reach out if you guys have any questions.